Hi, I'm Randall Heyman, a university mathematics academic. If you'd like me to make a video for you or your students during the coronavirus outbreak, then just comment me under any of my videos, or you can email me at coronahelpmathematics@gmail.com. Primary school, secondary school, or university level mathematics. It's all fine by me, whatever suits you. Okay, so this is the second video in about principal ideals. I've got up here the definition. I just want to point out, I've used the definition in Freilich. This commutative ring here, it means, as I explained, it means that we can change the order of multiplication. It doesn't make any difference. But if you don't have commutativity with the ring for multiplication, then you can still get a principal ideal, but in that case, it'll be either a left or a right principal ideal. So just be aware that this is something I haven't discussed in the videos, left principal ideals and right principal ideals. Okay, so someone has asked me, someone from the US has asked me about these principal ideals, and in particular, they're asking me questions about things like, I think they did ZL, I think they were talking about ZL, I could look it up actually in the email, but I think it was 11 and 14, and some questions about principal ideals there, and actually some questions about prime ideals. I've done some videos on prime ideals, so I think with what I do here, this should help answer these questions. I'm not actually going to specifically answer the questions that were asked. I'm going to do simplified cases, and this is actually a good thing in mathematics. If to do multiplication tables here is quite involved, so just do something simpler. So why don't we look at Z5 and Z6? And so let's do that. So I'll take here. So let's start with Z5. We take the numbers 0, 1, 2, 3, and 4. 0, 1, 2, 3, and 4. And we multiply, but remember these Z5, Z6s, Z14s, where we've got the number down the bottom. It's a subscript, not a superscript or whatever. It's a subscript. Well, this means that we're in modular arithmetic world. So all addition and multiplication is going to be done modulo whatever this number is here. So in this case here, all addition and multiplication is modulo 5. So if I multiply here this 0 by everything, I'll just get 0. So that's pretty dull. If I multiply 1 by everything, I get 0, 1, 2, 3, 4. If I multiply 2 by everything, I get 2, 2, 2 by 2 is 4. So that's 4. Now 2 by 3 is 6, but remember we're dealing modulo 5. So this will be 6, which is 1, and 2 by 4 is 8, which is 3. And look, we could stop, we'll stop there. Now, let's look at either the 1 or the 2, doesn't matter. Let's look at 2. What can we say about 2? So this is the ideal generated by 2, which is all the elements of R times 2, where R, that dot actually should, I'm getting a bit lazy with my dots. The dot should actually be in the middle, not lower dot. R times 2, where R is an element, is any or every element of Z5. So in multiplying here, R by 2, all we're doing is going across this line here. And you can see here, this actually turns out to be the set. It's every element of the set. So it is actually just Z5. So I think that this, the ideal generated by 2, is actually, well, it gives you Z5, which is certainly an ideal in Z5. And so that would be a principal ideal. Okay, now let's have a look at Z6. And I suppose the distinction here between 5 and 6 is that 5 is a prime, 6 isn't. So here now we're looking at Z6. So here, we'll look at the ideal generated by 2 again. 2 by 0 is 0, 2 by 2 is 4, 2 by 3. So let's just slow down. 2 by 3. Well, that in school arithmetic is 6, but remember we're dealing modulo 6. So this actually becomes 0. Then we go 2 by 4. 2 by 4 is 8, which is 2 modulo 6. And 2 by 5 is 10, which is 4. So notice what's happened here. This is just the set 0, 2, 4. So this is now not equal to, so what I'm saying is you don't always get the whole ring. In this case, we've got an ideal that is just part of the ring. And you can actually check if you want that it's an ideal because when we multiply, well, you'd have to go down and do the same for 4 and for 0. And you'll see that when you multiply any of these by any element of Z6, that you'll end up with 0, 2, or 4. In other words, 0, 2, or 4 is all you'll get. So it is an ideal, and it is generated by 2. But of course, the important point here is that this is not the whole Z6 yourself. Like we saw before, actually, when you're in Z5 back here, it turns out that except for the 0, and where you just get zeros, all of these here, this is the 1 or 2 or 3 or 4, actually, all of them will give you the entire ring of Z5. So I hope that's helped the person who asked me. That should give you enough to work through it. And if necessary, I would actually encourage you to do a whole multiplication table for Z14 and Z11 and actually work through it and look at every line and see what conclusions you can come to in terms of what are the ideals created by some A where, A is an element of, say, Z14. Okay, that's all I wanted to say. Any questions on principal ideals? Or in fact, any area of mathematics, comment me or email me at coronahelpmathematics@gmail.com.